Data races occur when at least one thread tries to modify a variable, or some other data, and some other thread tries to read it. Or that both try to modify it. So if both perform this, then it may end so that the final value of this is not 2 if it was 0 from the beginning. It would be 2 if this add instruction would read, modify and write back atomically into memory, but that's not the case. One way to make this to make it predictable is to use atomic int, the type, instead of int. But if we don't do that, we actually in C and C++ have a very serious bug called undefined behavior. That's one example of a serious bug. We will see very detailed rules of when a data race occurs in C and C++. But that's sufficient for now, this explanation. So how can we avoid data races? Well, we can read the source code, write the source code very carefully and avoid it. But there are also two tools that are useful, namely the Google sanitizer and a tool for Helgrind. Some people pronounce Helgrind using English pronunciation, but since it is a protection of Valhall in Nordic mythology, I call it Helgrind. Okay, let's see what they can do. Better to have the correct computer. Okay, so let's compile. Well, we should see what this does. It's basically the count example that we saw, and we create some threads, and when we create a thread, we give it the name of a function that the thread will execute, and then it does that and terminates, and the main thread waits for it, and the count is printed. Okay, so race and pthread and a.out. Actually, it's highly unlikely that there is some other output than 4. And the reason is that usually, this work is so little. So one thread is typically completed before the next one starts. So therefore we get the correct output. But this is also the frightening part of parallel programming. Just by looking at the output and see that it is correct does not mean that the program works. Okay, so what can we do instead? We can run this. Well, I should first compile it with debugging info so that the line number information is put into this a.out file. Okay, and now we run it with Helgrind, and well, it says that there is a possible data race. Okay, so that's very important to see. And it also says that it's 0 bytes into symbol this variable. Okay, so that was good. Google and many others have used Helgrind a lot, but Google realized that, I mean, not only they realized it, but they did something about it. Helgrind is extremely good, but it's approximately 100 times slower than running the program directly on the machine. So what Google did was to create something, a sanitizer, which is an extension to GCC and Clang that produces special code to detect certain errors. So if we compile it like this, well, we can just add here sanitize, and then there are different options, and no, and we say thread. Okay, so what will happen if we run this? It will complain. And as I mentioned, Helgrind is approximately 100 times slower. For one certain, not the thread version, but another part of the sanitizer, it was measured for many programs, and it turned out to be 76% slower than running it without these checks. So it's really fast. Okay. Let's now look at what problems we can have if we take locks in the wrong order. Deadlock. Well, what is this? It is another work function, namely that if we have, well, there are two different versions. I mean, it's a selection here, and either we take the lock A first and then B, and then unlock both, or we take B first and then A. So if one thread gets here and takes A and then wants to get B, but another thread gets here and takes B and wants A, sorry, then they will be waiting for a long time. So let's see if we can get some useful information. Pre-thread and deadlock and -G. Okay, so first we run the program and see what happens. Okay, we should say how many threads we want. Let's say we want 10 threads. And in this case, there was no deadlock. All threads happily say they got both locks. Okay, and that is not to say that our program is in any way good. So what we can do instead is to run Helgrind. What does it say? It complains. Namely, it's the lock order that was violated. What the Helgrind does is not to wait for a deadlock and say, now we have a deadlock. What it does instead is to observe that all threads get the same locks in the same order. And if they do, there cannot be a deadlock due to these two locks, since there can be no circular weight. So this is much more useful information than just getting to know that we had a deadlock in one execution out of 1 million, for instance. Okay, and let's try also the sanitizer. Okay. Now we can take fewer to get less output. Okay, so it prints a similar information. Some were happy, and then there was a lock order inversion. Okay, so this is these are invaluable tools. And if you use a language which do not have similar tools, it may be a good option to rewrite your code, bug and re-implement each bug, and then try it in C and see if you can get help from one of these two tools. 1 year we had first in one lab to parallelize a program in Java and then to parallelize it in C. And a group made a quite complex Java implementation which didn't work. And what I told them was to don't fix the bug. Wait until next week when you do the C version, and they should then, of course, implement exactly the same code, so to speak, and then they could fix both labs extremely easily. They could see immediately what was wrong. So using the right tools is really important. Since, I mean, it's always important, but it's even more important for parallel programming due to the non-deterministic nature of executing parallel programs. Okay, that's all for today, and next video we will, next lecture we will start with Akka. Bye bye.